This is Physics 2120, Lecture 18, and today we're going to continue to talk about Faraday's Law. Now, as we began talking about last lecture, an electric field is created in a conductor whenever we have a changing magnetic field. This happens even in the absence of a conducting loop. And a changing magnetic field will generate an electric field in empty space. And this induced electric field is non-conservative, unlike electric fields produced by stationary charges. The EMF for any closed path can be expressed as the line integral of E dot ds over the path. So Faraday's law can be written in a more general form that states that the integral of E dot ds is equal to minus the time rate of change of the magnetic flux. The induced electric field is a non-conservative field that's generated by a changing magnetic field. The field cannot be an electrostatic field because if the field were electrostatic and therefore conservative, the line integral of E dot ds would always be zero, and it isn't. We can use this in problems. So let's look at a solenoid. If a long solenoid, radius r, has n turns per unit length, and a time-varying current that varies as I is equal to some maximum value cosine omega t, where I max is the maximum current and omega is the angular frequency of the alternating current source. Determine the magnitude of the induced electric field inside and outside the solenoid. So, let's first consider inside. We know that the integral of E dot ds is equal to the time rate of change in the flux. So inside, we're going to be drawing our path of integration actually inside the solenoid. So first, d flux dt. We know that the flux is b times pi r squared. That's the magnetic field strength, which we're not sure what it is yet, times pi r squared. That is the area of the loop that we're drawing on the inside of the solenoid. Well, that's going to be constant, so the only thing that can change is the magnetic field. Now, from symmetry, we know that E has to be the same at different distances from the center of the solenoid, so the integral of E dot ds, E is constant, comes out, and it becomes the integral of ds, which is just the circumference of the circle, so it's E times 2 pi r. So E times 2 pi r is equal to minus pi r squared dB dt, or solving for electric field, we have the electric field is minus r over 2 times dB dt. We remember that the magnetic field from a solenoid is mu naught n I, which in this case is mu naught n I max cosine omega t. We're taking the derivative of that, we get the final electric field of mu naught n I omega over 2 r sine of omega t. If we repeat this now for the outside, we have the same starting equation. E dot ds is equal to the time derivative of the magnetic flux. And the time derivative of the magnetic flux this time is d dt b pi capital R squared. And it's capital R squared because the magnetic field is confined inside the solenoid. Even though my path of integration is on the outside, the actual flux is only on the inside. So the area that the flux goes through is pi capital R squared. So we get minus pi r squared dB dt. The integral of E dot ds is still the same, E times 2 pi r. So E times 2 pi r is minus pi capital R squared dB dt. So this time, the electric field goes like 1 over r. And so we have r squared over 2r dB dt, and plugging in what we had before dB dt, knowing the magnetic field is mu naught n I, and we get our final mu naught n r squared I max omega over 2r sine omega t. So in both cases, the electric field varies like the sine of omega t, but on the inside, it's going to increase as the electric field is going to increase as you go out from the origin, and then once on the outside, it's going to decrease like 1 over r squared. Now, one example of a real situation where you can see this happening is something called an induction coil. where I have a solenoid here, and I have it hooked up to some sort of power source. And when I close the switch, I get a magnetic field that is induced there. That causes a change in flux through this metal ring. That metal ring then, if there's an electric field around it, causes an electromotive force. I get current going that opposes this magnetic field, and I will shoot that metal ring right off of the end of the induction coil. Now, an electric generator is a device that makes use of Faraday's law. They take energy in by mechanical work and transfer it out by electrical transmission. And an AC generator consists of a loop of wire that's rotated by some external means in a magnetic field. So here I have this loop of wire, and I'm inside this magnetic field, and I can complete the circuit by making something called a slip ring. A slip ring is just a ring that's attached to the rod, goes around, and then I have a metal brush that just slides along it to create the electrical circuit. So we can look at a rotating loop in a magnetic field to see how the current flowing through it would look. Let's have a loop that's got N turns, all that have the same area, and it's rotating in a magnetic field. The flux through the loop at any time t, flux is the magnetic field strength times the area of the loop times the cosine of the angle between them. So in this case, if it's moving at a constant angular rate, theta is omega t, so it's BA cosine omega t. The induced EMF in the loop then is N d flux dt. So we take the derivative of the cosine, we're going to get a sine, and so we get NAB omega sine omega t. So this is a sinusoidal electromotive force. The maximum value is NAB omega, and then it's going to vary with frequency omega. So if I had this generator and it was turning around, and as it turns around, the field goes, we have a constant magnetic field through here, but the angle between the plane of the loop and the magnetic field is changing. I get a maximum voltage, and I get this sinusoidal current that comes off and lights up the light. Now, the maximum voltage is going to occur when omega t is equal to 90 degrees or 270 degrees. And that occurs when the magnetic field is in the plane of the coil and the time rate of change of the flux is at a maximum. And the EMF is 0 when omega t is 0 or 180 degrees. That occurs when B is perpendicular to the plane of the coil and the time rate of change of the flux at that moment is 0. So let's look at a real situation. An AC generator consists of 8 turns of wire, each that has an area of 0.9 square meters. The total resistance of the wire is 12 ohms. The loop rotates in a 0.5 Tesla magnetic field at a constant frequency of 60 Hertz. What's the maximum EMF? What is the maximum induced current when the output terminals are connected to a low resistance conductor? So first we need to know what omega is. Omega is 2 pi times the frequency, so 2 pi times 60, or 377 radians per second. This is the angular frequency of all the power that's used in the US, 377 radians per second. So the EMF we said was NAB omega sine omega t. So in this case we plug in 8 turns and our area and a magnetic field and omega, we get 136 volts. So the maximum current is going to be the maximum voltage over R. So 136 volts over 12 ohms, we get 11.3 amps. I can use a similar setup to create a direct current generator. Essentially has all the same components as the AC generator. The main difference is that the contacts to the rotating loop are made by using a split ring called a commutator. And so as this is turning around, the brushes are going to be attached to opposite sides of the loop. So when the current is supposed to switch directions, the other side of the commutator will be on that brush, and it keeps the current moving in the same direction each time. So in this configuration, the output voltage always has the same polarity. It's essentially looks like a rectified sine wave. So it's always positive. So instead of going negative like the AC, it's going the same direction. And so I get a voltage that looks like that. And to obtain a steady DC current, commercial generators use mini coils and commutators that are distributed slightly out of phase so that when you add them all up, you're going to be getting a constant electric voltage across the entire time. So again, as this one goes around, because of the split rings, as it changes direction, as soon as the current changes direction in the loop, the brushes are on opposite sides of the loop, and so the current always goes the same direction down the wire. Electric motors are just the opposite of a generator. They are devices which take electrical energy and transfer them out in forms of work into mechanical energy. So a motor is really just a generator that operates in reverse. A current is supplied to the coil by a battery, and that causes a torque on the current carrying coil that causes it to rotate. And I can get useful mechanical work out of it by attaching the rotating coil to an external device. However, as the coil rotates in the magnetic field, it still induces an EMF. And that induced EMF always acts to reduce the current in the coil. We call this a back EMF, and it increases in magnitude as the rotational speed of the coil increases. So the current in the rotating coil is limited by the back EMF. And that term back EMF is commonly used to indicate an EMF that tends to reduce the supplied current. The induced EMF explains why the power requirements for starting a motor and for running it are greater for heavy loads than for light ones. So let's look at an induced current in a motor. Assume that a motor in which the coil has a total resistance of 10 ohms is applied by a voltage of 120 volts. When the motor is running at its maximum speed, the back EMF is 70 volts. Find the current in the coil, A, when the motor is turned on, and B, when it reaches its maximum speed. So, when it turns on, the EMF is 120 volts. We divide that by 10 ohms, and we get 12 amps. Now, when we rotate it at the maximum speed, the current through it is the same applied voltage minus the back EMF over R, so it's 120 minus 70 over 10 ohms, and you get 5 amps. So when the motor is first turned on, we get a much larger current flowing through it than we do after it's running at its maximum speed. Now, another thing that we see with induced magnetic fields is something called an eddy current. If I have a bulk piece of metal and it's moving through a magnetic field, there are eddy currents that are created that are opposite in directions as the plate enters and leaves the field. And eddy currents are very undesirable because they represent a transformation of mechanical energy into internal energy. Essentially, what happens is the current opposes a magnetic field. So, as the pivot swings into the field, there is a torque on it that actually forces the bulk piece of metal backwards and slows it down. And it actually slows it down as it's coming out. We use this a lot of times in things like mechanical scales or things that are oscillating. We want to damp out the oscillations. We put a magnet and a piece of metal through it, and we get it, that force always opposes motion, and we can get things to slow down and stop. So to review what we talked about induced EMFs, and we said that we get an electric field whenever we have a changing magnetic field. There does not have to be a metal present to cause that electric field. We talked about AC and DC generators and how they work and the similarities and differences between them, and how a motor is a generator acting in reverse, and finally we ended up talking about eddy currents.